Our next lesson in the unit on kinetics and equilibrium is going to be equilibrium 2, dealing with mass action. And the topics in this lesson are going to be determining KEQ, the equilibrium constant, and on equilibrium calculations. So we talked about KEQ, the equilibrium constant, in the last lesson. So the equilibrium constant is what basically tells us which side of the reaction is favored. Remember, we said that if the right side of the reaction is favored, if we tend to have higher concentrations on the right than on the left, then we have a larger value of KEQ. Typically is that if the left side's favored, we have a smaller value of KEQ. But we just said it exists. We haven't talked about why it exists or how to find it. And that's what we're going to deal with here. The equilibrium constant KEQ depends only on the concentration of each substance in the equation and also how much of that substance is there. And so we're going to sort of work this out, but to do this, we basically need to give a general example here. So the following general chemical reaction, the one that's basically right here, is that what we're going to say is the capital letters are basically elements. And so basically A, capital B, capital C, capital X, capital Y, capital Z are all elements here in this equation. And the lowercase letters are the coefficients. And so, instead of having, 2H2 plus O2, this would be the same as having, A times capital A plus B times capital B right here. It basically works sort of the same way. That's all we're doing here. If this is true, that we have these guys out here, the equilibrium constant would be, KQ, would be as this equation has right here. The concentration of element X raised to the X power times the concentration of element Y raised to the coefficient of Y power. So that's concentration of X raised to the coefficient of X power. The concentration of element Y raised to the coefficient of Y power. The concentration of element Z raised to the coefficient of Z power. All that is on top. The reason why is because that's on the right side. Is that in the KEQ equation, all the values that are on the right side go on top and all the values on the left side go on bottom, which is why this is over down here. The concentration of element A raised to the coefficient A power times the concentration of element B raised to the coefficient B power times the concentration of element C raised to the coefficient of element C power. And we'll do an example of this. We'll do a few examples to show you how this works. But this is basically it right here. So this is the one you want to make sure you have written down here. Now, if we had fewer, in this case right here, we had, 3 elements on each side. If you had fewer than that, you'd simply cancel it out. You wouldn't include those here. And so, like, for example, if we had, AA plus BB plus CC yields XX plus YY, no ZZ, you'd basically, in that case, just don't use the Z there. It'd be just X to the X times Y to the Y over A to the A, B to the B, C to the C. So it's possible you might only have one term on top or only one term on bottom. If we had more than 3 products on each side, you'd put a 4th term on the top or on the bottom. And just remembering here, the square brackets indicate the molarity of each substance. These are concentrations in molarity. And so let's do a little bit of this to see how this works rather than just talk about it. It's a lot easier to sort of see this as an example than it is to explain it. So a container is measured to contain the following concentrations of gases: 0.366 molar H2, 0.443 molar O2, and 4.677 molar H2O. What is KEQ for this equation? And the equation we have is 2H2 plus O2 yields 2H2O, in this case where we have a reversible reaction. And of course, if it is not a reversible reaction, none of this actually works. So let's set this up. What we know is that KEQ is going to be equal to, we say on top or the right side. And so the only thing that's on the right side here is H2O. And so on the top will be the concentration of H2O. And it tells us the concentration of H2O is 4.677 molar. Now, we then say its KEQ is that's on the right side, the concentration on the right side raised to the coefficient power. Coefficient here is 2, so it'll be this squared. Divided by, on bottom, we want the first one here, which is H2, so the concentration of the H2 is 0.366 molar, raised to the power we have there. The power here is 2, is the coefficient there. I'm going to continue this out here, times the other guy here, which is oxygen. The concentration of oxygen is 0.443 molar, times the coefficient of this. The coefficient of the oxygen, it's not 1 there, so it's just 1. So it's like this. And so to solve for KEQ, all we really do is we say, get out your calculators now, and you would say 4.677 squared, because that's what's on top, divided by 0.366 squared, and then divided by 0.443 to the first, which is just 0.443. And when you do that, I get 368.6. So 368.6 for KEQ. Significant figure-wise, we got 3 sig figs up here, 3 sig figs right there, and 4 sig figs right there. So our answer should only have 3. So our final answer here would be KEQ is equal to 369. This is a unitless constant, so we don't have to worry about units on here, but this is basically how you go about finding KEQ, that you basically take the concentrations of the things that are on the right side, raised to the power of whatever they have, divided by the concentrations of the things that are on the left side, raised to the powers that they have out in front. And when you do that, that'll give you what KEQ is, however many you've got. And so that's how you'd work that out. So let's try another one. A 350-liter sealed container contains 15.6 moles of ammonia, 24.5 moles nitrogen gas, and 15.5 moles hydrogen gas. Presumably this is at equilibrium. I probably should have said that in the question. What is the equilibrium constant? And so first thing, we don't have an equation here. So the first thing we want to do is actually write what the equation is. We know we have ammonia, and so ammonia is NH3. And it's we have nitrogen gas and hydrogen gas, and thinking about those, we know that those basically is that ammonia is made of nitrogen and hydrogen, and so what's going to happen is this is going to be a combination of nitrogen gas, N2, and hydrogen gas, H2. Balance-wise, are we balanced right now? Nope, we're not. We got 3 hydrogens over on the left, we have 2 on the right, and so that means that we know that we're going to have to put a 2 out in front of this, that gives 6 hydrogens, and a 3 out in front of this, that gives 6 hydrogens, and now we have 2 nitrogens and 2 nitrogens on each side, so we're balanced now. So we're going to need to do this. Now to set this up for KEQ, KEQ is going to equal to the molarity of what's on the right, and the first one on the right is nitrogen. And so how much nitrogen, what's the concentration of nitrogen? Well, we say for nitrogen gas over here, we have 24.5 moles. But 24.5 moles isn't the concentration, it's the number of moles. To find the concentration, we need to find the molarity. And remember that molarity is equal to the number of moles of solute divided by liters of solution. And so in this case right here, the number of moles is 24.5, because in this case right here, the nitrogen is our solute. And the liters of solution, it's a 350-liter container. And so whenever you divide those out, I get 0.07. So for my first one, 0.07 is my concentration. For my nitrogen in this case, the coefficient of the nitrogen doesn't have a coefficient, so it's just going to be to the first power, or it really doesn't really, sort of, you can just ignore that if you want to, because its first power is the same thing as just the 0.07 by itself. The next one right here is the H2, the hydrogen here. The hydrogen, we know we have 15.5 moles, but we're going to have to go ahead and find the molarity. So we take the moles, the 15.5, divided by the number of liters, which is 350 still. And so I get 0.0443, 0.0443 liters, or sorry, molarity, so molar, 0.0443 molar solution, raised to whatever power we have here. In this case, that's the third power, like that, divided by what's going to be on the left side. And the left side is going to be the ammonia, the NH3. And in this case, do we know the concentration? No, but we do know how much we have. We have 15.6 moles. So 15.6 moles divided by the volume, 350, gives us a molarity of 0.0446. And it's going to be raised to whatever the coefficient is, which is the second power. Okay, now it's just a matter of just doing the math. So KEQ would be 0.07 times, to raise the first power, times 0.0443 to the third power, divided by 0.0446 squared. And in doing that, I get 0.003059, 0.003054. Now, significant figure-wise, 15.6 has 3, 24.5 has 3, 15.5 has 3, 350 liters has 2. Since all of them use that 350 liters and we're all multiplying here, our final answer is going to have 2 sig figs. And so our final answer for KEQ is 0.0031 would be what we get with significant figures here. So that's how you go about finding the equilibrium constant in that case. All right, so let's take a look at a little more sort of advanced version of this problem. The equilibrium reaction below is found to have KEQ as 0.369 when the concentration of hydrogen is 3.4 molar and oxygen is 7.9 molar. What's the equilibrium concentration of water vapor? And so we have our reaction down here, 2H2 plus O2 yields, reversible yields 2H2O. And here we know what KEQ is, but we don't know the equilibrium concentration of the water vapor. And so we're going to set up the equation the same way. It's the only thing is we just don't know one of our concentrations. And so to do this right here, we know the equilibrium constant is 0.369. So 0.369 is going to be equal to, we know we've got the H2O, it's over on the right side, which is what we're looking for. We don't know what that is. And so that concentration is just going to be x here. But since it's got a coefficient of 2, it's going to be x squared. And so we have x squared on top. On bottom, we're going to do the concentration of first the hydrogen. And so we know the hydrogen concentration is 3.4 molar. We already know what that is. So 3.4 molar concentration. Since hydrogen has a coefficient of 2, it's going to be squared. Then we have the oxygens, the other one that's on the left. The oxygen's concentration is 7.9 molar. And that's going to be raised to oxygen's coefficient is just 1, so we don't have to worry about that. And so at this point, we're basically going to solve for x. And so let's just sort of isolate for x squared first. And so we'd say the 0.369 times the 3.4 squared, and then times the 7.9. Doing that, I get 33.698. At this point, since it's x squared, we want to find what that concentration is. We just have to take the square root of that. And so we take the square root of our answer there, and I get 5.805. The unit would be, since this is a concentration, is molar. In this case, significant figures. Our KEQ has 3 significant figures. That should be a 3 right there. Looks like a 2. 3 significant figures. Our oxygen concentration has 2. Our hydrogen concentration has 2. So our final answer will have 2. And so we know we have 5.8 molar is the concentration of our water vapor here. And that's how you work that out. Of course, if we'd ended up with something where the coefficient of the water vapor was like, 5 H2O, we'd have to take the 5th root of this, which sort of doesn't happen that often, but that is how you'd go about working out that next section right there, if that's what you need to do. So continuing on this, let's try another one. Actually, that's what we got for right now. So that's basically how you set those up. So this is how you do basic equilibrium calculations.